We've now arrived at the final chapter of our course, Chapter 17 on Binary I/O. Way back in Chapter 12 we had some experience writing text I/O, that is, files that we could read in a text editor. Everything we wrote to such files, whether it be numeric values or strings or characters, were all ultimately converted to strings of some kind or visible characters. In other words, if we wrote the number 25 to a disk file, we didn't store it as a binary file or a binary representation of the number 25, but we actually stored it as the visible digit 2 followed by the visible digit 5. In other words, effectively everything we wanted to store would be converted from whatever native type it was into a sequence of characters which we call text and written to the file that way. In this chapter we're going to look at what happens when we have to write information to the disk more in its native form, that is, raw binary data. The author of your text attempts to make a distinction between text files and binary files by saying that in a text file data is stored in human readable form, whereas in a binary file it's not, and you have to use a program to read binary files. One might argue that no files are human readable. Ultimately, you always have to use a program to read them. However, sometimes that program is a simple text editor. And I suppose that's really the distinction. If you can open a file using a text editor and look at what's there and understand it, then it's a text file. The programs that you write in any high-level language have source code associated with them, or source files. That's the stuff you actually type in and use to code your program. Such files, of course, are readable by text editor. On the other hand, when you write a Java program and compile it into bytecode, then you have something that's no longer readable in a text editor. So one might wonder, why do we store things in binary files if they're so cryptic? And the answer is it's a matter of efficiency. For example, take the number 127 as a byte. In binary, its bit pattern is 0, 1, 1, 1, 1, 1, 1, 1. In other words, it's 8 bits, the first bit is a 0 and the rest of the 7 bits are a 1. That's a single byte. If you store that in its native form as a binary byte, it would take up exactly 1 byte in your file. On the other hand, as a text file, it would consume 3 bytes. You'd have to store something called the ASCII code for the digit 1, followed by the ASCII code for the digit 2, followed by the ASCII code for the digit 7, hence 127, and it would take 3 bytes in the file instead of 1. So obviously there's an advantage here when you store things in their raw binary form. They can take up a lot less space, and therefore they can also be a lot more efficient speed-wise when they're read into the computer or written out. Back in Chapter 12, when we talked about text I/O, one of the things I emphasized was that the file object does not actually allow you to read or write to or from a file. It simply encapsulates the properties of a file or path. So in order to actually perform I/O, you need to use a scanner or a writer as appropriate. So for example, to input from a text file, we may use the following 2 lines of code. First, we declare a scanner called input. We say it's equal to new scanner, and you'll notice the argument, which is supposed to be a file, it's an anonymous file, so we say new file, and then we give the name of the file. We then have a file object that the scanner can work on. In the next line of code, you see us actually reading a line of input from the file by saying input.nextLine, and we're simultaneously writing that out with a system out print line. To do this, we had to create an input object from an input class. And what that did for us is it effectively processed a stream of raw bits coming in from the file and decoded it as text. The story for writing is similar. We can't use the file object, but rather what we have to do is create a print writer of some kind. As you can see, the code on the bottom is what accomplishes this. We create a print writer called output, and you may recall that print writer's constructor will accept either a string or a file object. If it gets a string, it assumes that that's the name of a file, which it will then convert into a file object for use by print writer. In the next line of code, we would actually do a print line to the file by saying output.println, and then we would give a string. After writing, of course, we close the file. The author of your text makes the distinction between text files and binary files by saying that you can imagine a text file consisting of sequences of characters, whereas you can imagine a binary file consisting of sequences of bits. Later in this chapter, we'll demonstrate some binary and text I/O, and I'll give you a slightly different perspective on this. In any case, the number 12 is easily stored as a single byte when it's in a binary file, but in a text file it would be stored as two characters, one character representing the decimal digit 1, followed by a second character representing the decimal digit 2. As a single byte, which the author is viewing as a sequence of bits, 12 would be 00001100. And again, that would be a single byte stored in the file to represent that same value of 12. In any case, one thing's for sure, when you do text I/O, there's some encoding and decoding taking place. That's because the things that you're reading from and writing to the disk need to be always changed or converted into a sequence of printable characters. We have another example here, the number 199, which was again easily stored as a single byte in binary, but as a text file it's going to be stored as 3 bytes, a byte representing the printable character 1, followed by another byte representing the printable character 9, and the same thing yet again. These are shown for you in actually hexadecimal format in diagram A. You see where it says 0x31, 0x39, and 0x39 again. Those are the hexadecimal representations of the binary numbers that you see above the 3 arrows on top of each of those values. The 0x that you see is a standard for showing hexadecimal values. So anything that starts with 0x is understood to be a hexadecimal value. Hexadecimal means that the digits, instead of just going from 0 to 9, go from 0 to F. So in other words, they go 0 through 9 and then A, B, C, D, E, F. That gives you 16 different combinations to use. And hexadecimal means 16. Hex meaning 6 and decimal meaning 10. So 6 and 10, 16. You'll notice that you don't see any A's through F's in those particular numbers. They just happen to work out that way. And that's because the codes in binary that represent these printable characters of decimal digits from 0 to 9 actually start at 30 hex and go 31, 32, and so on up to 39. So it turns out that you don't need to get into the letters from A to F. But other printable characters, certain letters of the alphabet, will have codes that do have some non-numeric digits in their hexadecimal representations. The conversions that you see happening in diagram A are not necessary when we deal with binary files shown in diagram B. So in diagram B, the number 199 is simply written out as a byte, and here you see it in hexadecimal and binary format. The 0xC7 is the hexadecimal value, and the 11000011 above that would be the binary value. Now moving back to diagram A for a moment, the hexadecimal value you see there for the digit 1, 0x31, that would be 3 groups of 16 plus 1, and that comes to 49. So the decimal number 49 is the code, or the ASCII code, for the digit 1. On the other hand, the 0x39 is 3 groups of 16 plus 9 more, and that would come to 57. So 57 is the ASCII code for the decimal digit 9. Now moving back to diagram B, what is the 0xC7 that you see there? Well, the C, we ran out of digits, we got as far as 9, and we had to go to A, B, C. So A would represent 10, B is 11, C is 12. So we have 12 groups of 16 plus another 7. Well, if you multiply 12 by 16 and add 7, guess what you get? You actually get the number 199 to the far left of diagram B. So in other words, 199 is 0xC7 in hexadecimal, or in binary it's 11000011. I guess the important thing here is to notice that in diagram B, no conversion is necessary. The byte that you have is the byte that goes out to disk. Whereas in diagram A, when we're dealing with text I/O, there has to be an encoding and a decoding when you're reading to and writing from disk. Of course, even in this chapter at the very end of the course, we're still depending very highly on understanding objects. Here you see the inheritance diagram for all the classes that are going to be important for us when we're doing binary I/O. From the object class, we inherit input stream and output stream. From input stream, we have file input stream, filter input stream, and object input stream, and their counterparts in output are file output stream, filter output stream, and object output stream. And then finally on the input side, from filter input stream, we inherit data input stream and buffered input stream. From filter output stream, we inherit data output stream and buffered output stream. So we're going to be looking at all these classes and how we use them in the context of doing binary I/O. As it turns out, all the methods in the binary I/O classes that we're going to be using are declared to throw Java I/O exceptions, or at least a subclass of that particular exception. This is a checked exception, so we have to deal with it. And that means that we have to declare to throw that exception in the method or place the code in our code inside of a try-catch block as appropriate.